Bangalore. Really excited about this conference. Just wanted to tell you a little bit about the logistics before Srikanth gives his speech. Let me first, he's got a big one there. The organizers have to be introduced. So that's Srikanth right there. He's our leader. I'm Ranjini. That is Srikanth. This is Rituparno. We have volunteers who are kind of, could you just take a bow, the volunteers? You know, just maybe stand up and, yeah. Because if you need anything, you know, these are the guys and they've done a lot of work and, yeah, I asked them to, yeah, for identification. So, yeah. So, you know, so let us know if there is any problem. So we'll try our best to sort it out. So I should tell you a little bit about RRI. So we are now in the 77th year of RRI. RRI first started in 1948 with this building. And like I told somebody, the chairs haven't, you know, where you're sitting. I mean, these are all 78, 77 years old. They've just been polished and reupholstered, that's all. They really want to maintain it this way. So we started with this building, which is now called the main building. The first department was called the Liquid Crystal Laboratory. That was because of Raman's love for colors. And now we are called the Soft Matter Department, where we have 5 experimentalists and 1 theorist. So the ratio, you know, the experimentalist-theorist ratio in this conference is a bit poor, and, you know, it is not really commensurate with what we have in our department. So I'm really glad that Luca made it, because his flight got, yeah, his flight got cancelled. And so the next department was astronomy, which is the same department, the same building that houses the library, and you're having your breakfasts and lunches there. Okay, so there they do multi-wavelength astronomy. We co-run some observatories all over the country. The next department is theoretical physics, which is here, west of us. So there they do from gravity, relativity, open quantum systems, biological physics, statistical, theoretical statistical mechanics. So that's RRI. We'll do a little better than this because C.V. Raman was he has one of the biggest private collections in the country. So we have a Raman museum which is right here, and there's a little bit of time in our itinerary when we'll take you there. There's also going to be some Carnatic vocal by Anup there. So there'll also be some music. Okay, Sarika, you want to sing too? Okay, so you know, if anybody else wants to perform, we have time for that. There's Anup. Sorry, okay. You didn't give us your abstract. Okay, so Hindustani vocal, so that's wonderful. And so that's RRI, and regarding logistics, most of the lunches and, all the lunches and breakfasts will happen where you just had your breakfast, so that's called the Library Block Lecture Hall Terrace. After Itamar's talk on Wednesday and Sid's talk on Thursday, Sid's going to come in tomorrow. So those dinners, which are slightly bigger, so that will happen downstairs in the lawn. Okay, and there's a hurricane coming to Tamil Nadu today. We hope it's not going to rain, or if it does rain, that the rain stops by Wednesday. So, okay, with that, I'll yield to Srikanth.
Good morning and welcome to everybody. Let me start with a correction. I am involved with the organization, but the real organization was all done by Ranjini, Rituparno, and Srikanth, RRS for short. And they've done it with an efficiency that recalls to mind another organization with a similar initials. RRI, the host institute, has been very generous with its support for this meeting. So let me start by thanking both the co-organizers who've done the real work and RRI for their support. So I want to say a little bit about this series of meetings. Before we started, I actually made a lot of notes because I was told 15 minutes, but I'll keep it to 5 minutes. Basically, this is a meeting that started in 1999 in Trieste, which was co-organized with Silvio Franz and Sharon Glotzer. And there have been subsequent editions. This is the 8th. So roughly every 3 years, we've had these series of meetings going on. First in Rome in 2002, then we here in Bangalore in 2004, Kyoto in 2008, Paris in 2011, Aspen in 2015, and Bristol in 2018. So there was a break during the pandemic year, so this meeting is sort of a restart of that series. And apart from the meetings themselves, which have brought together a community of people who sort of interacted with and worked together, there have also been 2 special volumes arising from the 99 and the 2015 editions. And also, I'm very proud of a brief lecture notes that was published in JSTAT coming out of the 2004 edition, which had lectures by Francesco Shortino, Dave Dreichman, and Patrick was a co-author, and Giulio, and I'm blanking on the last one, but there were four of them, and these are Andrea Cavagna on the peace spin models. So these have been actually used quite widely by the students coming into this field. These meetings have sought, as the name suggests, to focus on unifying or universal aspects of the glass transition, or of glasses, of glass physics, and a lot of the focus has been on core topics like the glass transition, slow relaxation, aging, and so on. But it has also included, to some extent, related topics like in jamming and polymers and other soft matter. There has been relatively small representation of what goes under the heading of glass science, work that addresses the making and the properties of real glasses. And I was telling somebody recently that, to paraphrase Bernard Shaw, the glass physics and the glass science communities are 2 communities that are divided by a common subject, which we hope we can do something to bridge. So it's nice to see that several people who've been involved with the previous editions are here. There's Paddy Royal, Peter Solich, Patrick Charbonneau, and Giulio, who've been involved with organizing the previous editions, but also people like Gilles Tarjus, Chandan Das Gupta, Ludovic Berthier, and Bulbul Chakrabarti, who've been participants in the previous editions. And so for those of us who've been at these series of meetings, we've been witness to substantial progress that has been achieved in addressing these focus problems in glass physics. But people may feel or may not that there are many fundamental questions that remain to be addressed, and work will therefore go on. Many people will keep busy in addressing these. But one may also wonder about how the enthusiasm for these problems and the momentum in addressing them will be in the coming days. So one of the things that we're going to do is to have a sort of a focused panel discussion on this on the last but first day on Thursday, I believe. Given that kind of a perspective, one of the things that we tried to do here was to sort of try to go beyond topics that go under the heading of sort of unifying themes, but at the same time also form an essential characteristic of the glass problem, namely that it informs thinking in a diverse set of domains, from computer science, machine learning, memory and learning in general, active and biological matter, etc. So we've sort of, in addition to having talks in the core areas or themes that I mentioned. We've also attempted to include discussion of these other themes. And also, as I already mentioned, there is going to be some representation of glass science, and it'll be interesting to see if a better interface with problems in that area will lead to new and interesting questions for this community. So there will be overview talks, Gilles Tarjus on the mean field theory of the glass transition and beyond, Giulio on machine learning to statistical physics of glasses and back. I was reminded of Bilbo, there and back again. I don't know if that was in the back of your mind. And Anup on machine learning explorations of disordered materials. There are special lectures that were already mentioned by Itamar and Sid Nagel, and the panel discussion that I mentioned a moment ago. So I hope you'll all enjoy the meeting. Welcome to everybody. And once again, all thanks go to Ranjini, Santhan, and Rituparna and the RRI team. Yeah, thank you. So, okay, I stay here. Okay, but Itamar, do you want to set up your talk? It's okay. Yeah, it might help, but it's okay. I'll just pocket me. Okay, so that's all right. Okay, so we begin by a talk by Itamar Procaccia from the Weizmann Institute. Itamar needs no introduction. He's well known for his work in several areas of statistical physics. And over the last many years, he's been looking at problems related to yielding, plasticity, and in glasses, and most recently he's been looking at building up theoretical framework for anomalous elasticity in amorphous solids. So today he'll tell us about the analytic theory of shear localization in cuvette geometry.
Thank you, Srikanth, and thank you for inviting me here. Actually, coming here for me is especially pleasant because I spent here some decades ago, really looks like an infinite past, as the Raman professor, and I learned to love this campus, so it's very nice to come back. Especially, I have to say, I arrived yesterday late, and I was offered a dinner. It was exactly the same dinner that I had, I don't know, 30 years ago, 35 years ago, Etali, you know, with yogurt and rasam and this and this. And I recall that in my last visit, by the way, I loved it. It's very tasty. I recall that in the last time, it was the same dinner in the first day, and then the second day, and then the third day. And then I realized for the first time there's something that is called meat withdrawal symptoms. Because I remember very well, in the fourth day, I had a meeting with Madan. And while I was talking with him about very interesting things, I was hallucinating about a steak coming in the air with a glass of wine. And Madan looked at me, he saw that I'm a little bit different. And I experienced this for a long time. I'll not tell you more about how I tried to resolve it, because it's very difficult there. At that time in Bangalore, there's only one place that offered meat in a restaurant, and it was called The Only Place. Anyway, so it's very pleasant to come back here, and I'll use the opportunity to bore you with some recent stuff that we've done. This is work that I've done with my colleagues in China. By the way, for those who don't know, I'm involved now in building up a new research center in Hangzhou. In Hangzhou, we're building a research center to the tune of $1 billion by the Beihang University. And I believe it's going to be a very interesting place for people who want to, in the future, come and visit. So Fu Yang is my postdoc there, and my colleague Yulian Jin from Beijing were very useful in developing the work that I'm going to describe. So I want to talk about Couette geometry. Now, Couette geometry, you all know, Couette geometry has, in 2 dimensions, has 2 disks with material in between. In 3 dimensions, is 2 spheres. And you rotate one at one speed and the other at one speed, or you can do it also quasi-statically, as we do it here. So what does it mean quasi-statically? I will explain. Firstly, let me say we have a material here that is made of disks of 2 radii, 1 and 1.4, the classical thing, bidispersed. In the simulations we're going to describe, there are 3,534 50-50 bidispersed disks. And the material that we consider here is relatively ductile. That is to say, we create it, but we don't do swap and all these things to make it very brittle. For reasons that I'm going to explain, I want to use still what we call linearized theory, which will be relevant for ductile materials. So the 2 concentric rings are of radii 58 and 168, and this is the material inside. And now the inner ring is rotated quasi-statically. What does it mean? For those who don't know, you rotate a little bit and then you energy minimize. You rotate a little bit and you energy minimize. So you do it quasi-statically, such that after every step, the system is brought back to mechanical equilibrium, and the changes are in angle delta theta, very small, 0.0, 0.24 degrees. Okay, so very small, very small, very small. Still, you accumulate stress. Now, why this is not doing me the usual thing? I want to go, how do I do this? Wait. Usually there is a little gizmo here that does the, where is it? Well. Here. No, do it again here. Yeah, here. Okay, great. Okay, so Couette geometry, and now when you do this, you measure the stress, and you've seen this many times. So the r theta, the component of the stress, which is the shear stress, the coordinates here are the angle and the radius. You have the usual thing that the stress is increasing at the beginning, looking sort of elastic, and then you have all these drops and the plastic drops. And what we want to understand is what happened at one of these drops. So we are interested in the displacement field during a stress drop. Why displacement field? Because it's measurable. Okay, so, and when you have a displacement field, you can break it into 2 components, the radial component and the angular component. Both of them are functions of both the radius and the angle. And in particular, I would like a theory for the angle average, tangential, and radial components. So this is the angle averaging. You do the quantity averaged over the angles, and you get a function of the radius alone. So both the angular component as a function of r and the radial component as a function of r. And I want to have a theory for those in order to understand what is going on. So what is the challenge? Challenge is, here is an example of the angular part of the displacement field as a function of r. This blue line, embarrassingly, is the prediction of elasticity theory. Whereas the data that you see are these black dots, and the line that goes through them is the theory that I'm going to describe. So the point is, and to the eye, what you see in a situation like this, you see that part of the system, when you drop, rotates in one direction, and the other part in another direction. That is to say that the displacement field, the angular part, shows what we call shear localization. That is to say, there is a shear localization in the borderline between the red and the blue, which are the 2 directions of rotation. So pure elasticity would predict that the that the radial derivative of the angular component of the displacement is going to be the blue line, and this is what you actually measure, and this is actually what the theory is. And the peak here, or the dip if you want, is the shear localization that we want to understand. So if elasticity theory were applicable, what you need to solve is a well-known equation that you can find in Landau and Lifshitz for the displacement field. So is the shear modulus, the Laplacian of D, lambda plus mu, the two other moduli, the Lamé moduli, the gradient of the value of D equals 0. And this, with the boundary conditions that we now have, the radial component is 0 at R in, whereas the angular component is not 0 because we are rotating there. And at the outer ring, they are both 0. So, you know, you have an exact solution that you can immediately write down for the angular displacement as a function of R. It looks like this. It solves the boundary conditions, and the number here is determined by how you do this delta theta. So it's a very small omega 0 because delta theta is small and you have a factor of 180 here, etc. So this is the result, the blue line. The blue line is what you expect, and of course the conclusion is that clearly wrong prediction. So you need to come up with a different theory. So elasticity theory, as it is in Landau-Lifshitz, fails to predict the correct displacement field, so we need to do something else. Now I want to drive a theory to explain the observed phenomena. Why do I stress this? Because it was said already by George Box that all models are wrong. And indeed, sometimes they're useful, but nevertheless, we want a theory in the sense that once you have a theory, you can apply it not just to this thing, but also to other situations in which you have strain, stresses, and amorphous solids, etc. So how do you do this? To develop appropriate theory, we need to take into account quadrupoles and dipoles. And I've said it already, as Srikanth said, for a number of years, but the point is that plastic events, what happens in amorphous solids when you have a plastic drop, always involve these objects which appear in the displacement field. And I want to stress again that elasticity theory protects both monopoles and dipoles. That is to say, you cannot do in an elastic system, even in an amorphous solid, you cannot just expand somewhere because the pressure will push you back. You can also not pull particles and move them out because due to the Poisson effect, other particles will come in. So the cheapest thing they could do is a quadrupole. So you cannot make locally a monopole or a dipole. In the same way that in elasticity theory, you cannot do a charge locally. You can only do dipoles. So electrostatics protects only protects monopoles, but does not protect dipoles. Elasticity protects both monopoles and dipoles, and the cheapest thing that you can do is create quadrupoles. And indeed, quadrupoles are there. Since I have a short talk here, I'm not going to show you all the evidence. I'm going to say more about this on Thursday. But you can have stuff. So since the protocol is quasi-static, now I have to add some things in order to tell you how to do a theory of all this. So some preliminaries. Since the protocol is quasi-static, the stress that we are building behind when you do this step-by-step thing is divergentless, because you do bring the system back to mechanical equilibrium after every step. This is important, and this was not used in previous theories that we've done when we didn't look at accumulated stress. Since the steps are small, we are going to assume that the relation between the strain field and the displacement field is still linear. That would be untrue if the system is brittle. And for brittle systems, you have to go further, but we are going to do this for this ductile case. And last, that you can still use the linear relationship between stress and strains is the classical relationship with A is the tensor of moduli. Okay, and then in that case, you can write the energy of the system in terms of the background stress sigma times the little strain that you made in the last step. Okay, so the U is small, is the last step. The background is there, but I have to stress, neither stress nor displacement are state functions. They're always being measured with respect to a reference state. This, the stress is a state function, so there is a meaning to the background stress. But the strain is only the strain of this very step that I'm looking at. So we have the contribution of the elastic energy from the background times the little u, and the stress that you have made or lost at the present step times the same u. Yeah.
What's the distinction between the capital and the small?
So the capital thing is the background that you have built up. Okay, when you look at this thing here, okay, so you have a stress that you have built up. So for example, when you look at this drop that I'm looking at here, you know, there is a background stress, capital sigma. But there is the actual displacement field that was made here. The gradient of the displacement field is the strain, and the stress is A times the strain. Okay, so that's this small one that you've made now. Okay, so there are these two components. And then you have to take into account the quadrupole interactions, and you have to take into account the cost of the quadrupoles, which is the quadrupoles times the strain, and these tensors that are connecting them at this point are not known. I can say more about this later, but this is the minimum that you can do. In fact, this is not enough, and I'll show you in a moment what you need to add to this, but this is the beginning. In order to do this, in order to show that the background stress falls when you do a theory. So now what you need to do, you need to minimize this. You need to minimize this in order to find an equation for displacement field. So to derive, not the equation of motion, I'm sorry, the equation for the displacement, we need to minimize the Lagrangian. We have to vary with respect to the Q field, and when you do this, you get a relationship between the Q field and the strain field, showing that the Q field is not just a random field, it is actually determined by what happens in your system, and this is a generic thing. And then the variation with respect to displacement gives the variation with respect to displacement gives an integral like this. And now you need to use the sigma tilde is really a combination of the renormalized stress, the background stress, plus the contribution from the quadrupoles. And when you now say that the variation of the stress is determined by the variation of the displacement because there is a linear relationship between this and this, now you integrate by parts, and this d alpha is going to work on the capital sigma, and div sigma is 0, so it doesn't matter. And then the rest that is remaining is an equation on the divergence of this renormalized stress at 0, which is exactly the same equation that you can find in Landau-Lifshitz, except that instead of the sigma itself, it's a renormalized sigma. So nothing is changed by addition of quadrupoles, except that you have a renormalization of the moduli, and you have a renormalization of the distress because of this. But this is not enough, as I said. You have to add the dipoles. Now, what are the dipoles? I told you before that elasticity theory protects from dipoles. The cheapest thing is quadrupole. But if the quadrupolar field is not uniform, then you could have gradients of the quadrupolar field. And the gradient of the quadrupolar field is a vector, and this vector is a dipole, and you can show and prove that it has all the properties of dipoles, Berger's vectors, and all this stuff. And then when you add this to the theory, I'm not going to now do the variations, etc. Believe me, the time we do it, you get a new equation for the displacement. So if this were not there, it'll be 0. It's the classical equation. But now you had an additional term due to the influence of the dipoles. And the additional term is linear in the displacement. And I'm stressing we are still doing a linear theory, still not doing nonlinear theory, and I'm going to say something about this at the end. But now look at this. What this does is dramatic, because in elasticity theory, displacement is always protected by gradients, in the sense that if I just take the system and move it, right, the displacement field is changing. Okay, so what is going on here? This system breaks translational invariance. In fact, it does. It breaks translation invariance. But worse than that, when you analyze this tensor gamma, at the beginning, when we started to develop this theory, we thought that this gamma is diagonal and has k squared, and 0, 0 here. It turns out that experiments and simulations show that this was wrong and that this gamma is more interesting in the sense that it's anti-symmetric. So if this term here is negative, this is positive, and vice versa, and can be either. And this, but can be either, or not either or. Let's say in one system it's either minus plus or plus minus, and this breaks chiral symmetry. So this thing is breaking chiral symmetry, and all these breaking of symmetries are associated with the dissipation. Let's say, as you know from the Nether theorem, when you break symmetries, you break conservation laws, and indeed the dissipative step that you show when stress falls is dissipative, and question was, where does it come in the theory? So this is where it comes. Anyway, so this equation, okay, when you write it in terms of the radial and the angular components of the displacement field, looks like this. So there are two coupled equations for the radial and the tangential components, and luckily we can solve also this exactly. Let's say this system is exactly solvable with the given boundary conditions. So again,
before this, dissipation was nowhere in your displacement.
exactly. So now we understand where the dissipation comes in, okay? Because, you know, and I have to say, this is a little bit tricky, because you are minimizing a Lagrangian. So this looks like a conservative system. But turns out that the breaking of symmetries that are involved appear in the theory and allow you for dissipation, and this is where it comes in. Okay, so now with the same boundary conditions, you can solve exactly. You predict that the radial component is 0, which is not so surprising because you only, the average, angle average radial component is 0 because you are only rotating the inner thing, and the angular component has this form in terms of Bessel functions. So this is the Bessel functions of the first kind, the J1 and Y1, and it depends on R in, R out, and the screening exponents. So these are really screening exponents. They have the dimension of 1 over length squared. You say this is del squared, so it's 1 over length squared d. So also this has to be 1 over length squared, and these are indeed 1 over length squared. These are screening exponents. And what determines the screening parameters? So we have now a question. You have screening parameters. How they're determined theoretically? And it turns out that the screening parameters are actually quantized in a funny way, in the sense that what is being plotted here is the solution, the analytic solution. Okay, the analytic solution, as you see, has a minus here, and the denominator can go through 0. This is where the system has a very huge response to the drop in the displacement field. So, and you see these Bessel functions, they need to fit boundary conditions. So the screening parameter kappa E is determined by fitting the boundary conditions, and there can be a few of these solutions when this denominator goes through 0, and it looks like this. So this is the maximal value of the solution of d theta, okay, the maximal value in absolute magnitude as a function of the screening parameter. And you see these singularities, and the blue points are now numerical simulations where you have the best fit to the solution. And as you see, they do concentrate around these peaks. That is to say, there's no question that there's nothing in the gaps. The fluctuations around these peaks are both due to finite size effect, but also to the miracle that the theory, it all works, because you're doing a field theory, which is long wavelength theory, on a system that is relatively small, so it doesn't fit exactly, but you see that it is really taking the essence of what the screening exponents are going to be. And indeed, the solutions that are concentrated here look like this. That is, you have the stress localization somewhere in the middle. Solutions that have this screening exponents, the shear localization is near the rotating inner circle, and both of these were seen in experiments and in simulations, so they're real. The last one, which is relatively rare, has two maxima in the function, so I'm not going to talk about them much. Let me see. So I really want to know the quantization, so to speak, of the screening exponents. It's not surprising. You have Bessel functions. You have to fit to boundary conditions. So this will pick up particular values, not any value that you may have in mind. Okay. I want to finish by just doing some propaganda about the paper that I'm writing right now these days. What will provide the theory of shear bending? So here, in this case, we've done shear localization. So the system was relatively ductile. The solution was smooth. The question is what you need in order to explain and theorize the phenomenon everybody knows, that has been studied so much by also many people here, which is shear bending, in which there is a very sharp transition in the displacement field, in the sense that part of the system is going this way, part of the system is going that way, or part of the system is not moving and the other part is moving. So first thing that you need to do is to go nonlinear in the relationship between the strain and the displacement. So this is the linear thing. The next thing is you have the nonlinear contribution in the displacement. Has to be there. If you don't do this, you don't get shear bending. And the next thing is when we introduce the dipoles. So the theory that I explained so far was up to quadratic order. That is, you have the displacement times the dipoles plus the dipole-dipole. These are all the terms that are allowed in the theory by symmetry up to.
Can I ask you one question?
Yeah.
Why is the Q term missing in this?
What? Say it again.
The quadratic term in Q is missing in this. P is
Oh, the Q only renormalizes things.
No, but when you put in a gradient of Q in a Lagrange.
This is the gradient of Q, the
I
P.
understand.
P is the gradient of Q.
I understand, but then I should have the mass term of QQ.
Yeah, yeah,
there. You
yeah.
couldn't have just taken it out.
It is here in the renormalized,
Before you put in the gradient, but once you put in the gradient.
also after.
I have to do it again with the QQ term in there
Yeah.
and the gradient of
Yeah.
Q term in there.
Yeah, but it does.
Then your solution will be different.
I don't think so.
It is.
Okay, we can argue about this.
So I'm just saying, I
Okay.
don't think it's adequate to say, okay, I have renormalized the QQ term, then I'm going to add a gradient term, and I'm not going to.
Okay, we can argue about it. I'm very happy to argue about this. Anyway, the point is that what I need to do now, up to above the linear order, I have to add the quartic term. The cubic term is not allowed by symmetry. And once I do this, after some substantial amount of work and calculation, took months, actually you understand that there is a zero mode of a Hessian, and that zero mode of the Hessian has a king solution, which is a shear bend. And maybe, hopefully, okay, also you can show that the width of the shear band varies with the values of the elastic moduli, so you can have a sharper or a more diffuse shear band depending on the ductility of the system. And maybe, hopefully, 15 years of research are coming to a switch conclusion, at least for me, in the sense that I started to work about this about 15 years ago. So hopefully, maybe we are coming to a point where I can say that at least I can understand this shear bend. So I thank you very much for your attention. Huh?
The previous slide. So, questions already? Okay.
Just
Yeah.
Well, I think it clarifies very much the discussion we had with about, for instance, the use of elastoplastic models to determine trajectories, which is a model which is wrong, as you said from the beginning, and I certainly agree with you. But I think that we're dividing the field into you trying to, by first principle theory, describe what happens in one step of minimization. This step can be dramatic because it can be an avalanche, it can be a shear band, which is even,
This is why you need to go
system
nonlinear.
size. But on the other hand, the background, what we're interested in I would say in elastoplastic models, is the evolution of the background stress. So something that, as a function of time, you get, and then you get the stress-strain curve, for instance. And that is something, I believe, that you cannot predict with your theory, even if you go nonlinear.
I didn't think about this. Frankly, I didn't think about it because I was interested in the displacement field to understand what happens in the event. But you could do this step by step, right? And step by step, okay. I think what you're saying is that you don't know whether in a given step of increase of strain, you're going to just go up elastically or you're going to see a drop. Right? This is what you're really saying, that you cannot predict a priori from the, let's say, the state of the material, whether an increase in strain is going to be associated with increase of stress, or whether, because of the increase in strain, you're going to see a yield with a, okay. But now, let me just say that in the case of brittle system, let's say if I take this seriously to a brittle system, the prediction is going to be there's going to be a stress yield. Let's just say that the stress is going to increase continuously with changing slopes though, because every step you're going to renormalize your moduli, and then there's going to be a drop at one point, as Ludo has shown numerically very beautifully. Right, so you're going to see in the very brittle case a less confusing trajectory. In the sense, it's going to be one drop, and the background stress where this happens is going to be predictable. This is where the eigenvalue of the Hessian is going to go to 0, and it's going to be one stress. So in that case, I think you do. For the ductile case, it's more difficult because you never know whether it's going to affect, whether it's going to be a elastic or a plastic step.
We have time. So,
Silke.
Jeppe.
Jeppe.
Yeah.
Sorry.
No, next, Silke.
Hello, yeah, very nice talk. So I was wondering, I think you could extend this to having something like an active system where you don't have internal just dipoles and quadrupoles, but internal, but essentially force monopoles, dipoles, or whatever higher order.
Very possible. Yeah. Very possible, and you're most welcome to try. I think that
we might have done the monopoles actually.
The approach is classical, right? I mean, people have done it in other subjects. You expand lambda Lifshitz like in whatever fields you need to take into account. So I think it's a very general approach. I'm pleased that it works at least in this limited form of quasi-static. There's a lot more to do. The moment that you don't do quasi-static, but you do time, hell breaks loose, and you need to do everything from the beginning.
Yeah, no, I think let's talk. I think we may
But
have something
quasi-static,
connected, yeah.
I'll be very happy to talk to you more about this. I think Jeppe was.
Yeah, so this is all formulated in 2 dimensions.
Yeah, no, can do it.
And my question is simply how much generalizes to 3 dimensions?
We have already generalized it into 3 dimensions. And in fact, the talk that I'm going to give on Thursday is going to show you that it works in 3 dimensions, which is amazing, because dipole-induced transitions, which are known in 2 dimensions as Kosterlitz-Towless and hexatic, are very well known in 2 dimensions that don't exist in 3 dimensions. This, which is also a dipole-induced transition, exists also in 3 dimensions. We see a phase transition. I'm going to talk about this on Thursday. There's a lot to say about the 3-dimensional analog.
Yeah, so Itamar, just,
Yes,
I haven't understood how do you have the second term there, because that breaks translation invariance. You made a comment on that.
Which one? This one?
The second term, yeah, which breaks translation invariance.
This one?
Yeah.
Because
No,
it's derivative
no,
of
it
P.
doesn't. It doesn't.
D alpha is, what
This
is
one, no, P is proportional to D.
No, D is the displacement, isn't it?
D is the displacement, and
Right.
P is the dipole field, but you can show it is linear in the displacement, so it's dd. So it doesn't break anything.
So that
Sorry,
doesn't break.
Itamar, this was kind of my question. That P is a derivative
Yeah,
of Q.
Yeah.
And you minimize with respect to Q,
I
right?
did.
This is why this is fine, because you
But
can
I
take
do,
the
yeah.
derivative of the derivative.
Okay, so it is
Q,
here.
Right, so Q is your
Okay.
fundamental field.
So it is here, yeah.
But it's not there because there should be a QQ term
But-
if you have a derivative of Q term.
I heard you. I'm happy to talk to you about this. I think that we've taken into account the QQ, but
Okay.
this doesn't break. This is okay by symmetry. The point is, you write the Q field and the P field, but they're not mysterious. The only thing that is really fundamental here is the displacement field. And as the stress...
And the Q field.
No.
You have two different.
Yeah, the only fundamental thing is the displacement field. Everything else derives from this. And you can find when you do the theory that the Q field is the tensor times the displacement field or times the strain field, which is a function of the displacement field. And the same thing is for P. And the P field is simply linear. There's a tensor times D. So it is morally the same as the displacement, so this doesn't break symmetry. It is okay. These are all the terms that are allowed by symmetry.
And have you checked the gradient of the antisymmetric part of the strain? So there could be local rotations
Sure.
in the system.
Sure, no.
So that would enter into the Lagrangian
Yeah.
also.
The gradient of the displacement field, the gradient of the strain field is determined by the displacement field. The displacement sees whatever happens there. So the strain is simply the gradient of the displacement field, or if you go nonlinear,
Yeah, okay.
also
We'll
a higher order.
talk.
Yeah.
Are there...
So one question is like if you, my understanding is your inner like geometry
Ring.
is rotating. So does anything change if you move the outer?
Yeah, it's going to be different, but you can do it. It's just a question of what boundary conditions you use to solve the equations. The equations are not going to change, of course. The equations for displacement field are what comes out from the theory, but then you need to solve them with boundary conditions. So if you do different boundary conditions, you could do also inflation of the inner ring, then you're going to get also a radial component. You could do all kinds of things, and we did. We looked at inflations, everything. And so it's just a question of what boundary conditions you use to solve the equations.
Can I ask
So-
a quick
Yeah.
Okay.
So you start off by defining this quadrupole field, which in 2D would come from writing down the curl of the stress tensor or the strain tensor, right?
Actually, I have a different way of extracting the quadrupole field from the displacement field, which I didn't explain. But you can extract it directly from the quadrupole,
I understand you can,
No.
but wouldn't it then imply that the compatibility condition on the stress is violated?
I don't think so. I think everything is not violated. And you look, you
No,
see...
no. What I'm saying, isn't that where the quadrupole comes from in plasticity theory?
No.
The Eshelby is the curl of the strain tensor is non-zero. That is how you get the Eshelby. That is plasticity.
I don't know, that's not how the way I think about it, but...
That's
you
how
know,
you introduced it in your paper.
Maybe,
Yes, right. But I'm saying if I now solve
I'm not
this
responsible for all
equation,
my papers,
but if I now
Too many
solve this
papers.
equation, the right-hand side is identically zero. So,
I frankly don't know what you're talking about, but let's talk about this in private, because I don't remember every step,
no,
So-
I'm trying to understand where the quadrupole came from.
The quadrupole came from vision. I can look at it and I can determine it. I can take the displacement field, analyze it, and show what is the part of the displacement field that looks like a quadrupole, sine 2 theta, cosine 2 theta, just the right way for the quadrupolar field. And I can just show it to you. And then take the gradient and show you the dipole field. Then integrate around it and show you it's a Berger's function.
No, that's all.
Yeah.
So Silke, ask the last
Yeah,
question, but
please,
I'll
yeah.
add a couple of riders to it before you can answer.
Okay.
Small one. So you get this chiral asymmetric term, yes? This reminds me of people playing with odd elasticity.
It's odd plasticity.
It's odd plasticity.
It's exactly the analog of odd elasticity, except that it's in the plastic response. You're absolutely right.
Yeah, thanks.
Okay. Yeah, so that was sort of unrelated to whatever I had in mind. But, you know, in terms of all this discussion about terms that should be there or not, I think you're still doing, in everything that you're saying, you're doing a quadratic theory.
No,
No, but with
yes.
But with
For this
different
talk,
fields
yes.
that
Yeah,
you
for this
think
talk is
are
all what
relevant
you
in the
need.
lowest order,
Yeah,
correct?
for the shear localization is
So-
all what you need, but for more you need to go further, yeah. So to get shear bending,
Yeah.
you need to go further.
Yeah. And I wanted to ask a general question about
Yeah.
if there are sort of these discussions about what terms should be there or
Yeah.
not, what
Yeah.
is guiding you? Because, that's...
Symmetry. Symmetry.
So, okay. So there is yeah.
You know, this is really classical physics, you know, this is classical theoretical physics. There's no mystery here.
Okay.
You use symmetry in order to know which terms are there. Gilles.
Okay. Yeah.
Gilles.
Go
No,
ahead,
say
go
it,
ahead.
Gilles.
No, actually, there's symmetry, but it's not completely first principle in the sense that you also need to define what other fields of interest.
Sure, you need to recognize it.
With the rule is you put the quadrupole as an empirical field that exists. And
Which I can measure,
exists.
which I can measure.
You take two fundamental fields,
Yes,
and then by symmetry you have
you're
all
right.
the terms.
You're right, you're right. You have to recognize what are the fundamental fields in the problem, but this is true everywhere. You know, I mean, you cannot do Wilson realization group without saying which are the order parameters, right?
Okay. With that, let's
Thank you.
close the discussion. Thank you, Itamar, for getting us going in a good way. Okay, so the next speaker is Juergen Horbach from Düsseldorf.
I'm Juergen from Düsseldorf.
I'm getting out of your skin in a second. I just need to.
Okay.
I think it's everything. Oops.
So like Itamar, Juergen has been familiar face. He's visited many times and collaborated with many colleagues in India. So he's going to tell us about macro versus micro-rheology in glass-forming liquids.
Yeah. Okay, first of all, I would like to thank the organizers for the invitation to this very nice conference. So I will present work that I've done in collaboration with Manoj Adhikari and Susmita Ghosh. Both are postdocs in my group. So it will be on rheology in glass-forming liquids. First of all, glass-forming liquids. So I always like this plot here for glycerol. So this is the relaxation time from different experimental techniques, dielectric spectroscopy and light scattering. You see on the y-axis, it varies from 1 picosecond to 5 hours. And so there's one temperature that I've marked here, so the mode coupling theory temperature, which marks the region where one has a gradual crossover, say, from a liquid to an amorphous solid-like dynamics. So in my talk, I'm especially interested in states around this temperature Tc, of course, for a model glass former, and far below Tc. So when one approaches here the experimental glass transition. However, I always consider liquids and not out of equilibrium systems. So I would like to address two different themes. One is on macroeology. It's a kind of proof of concept. So this is this plot from Barnes, from this article by Barnes. So this is a flow curve, say of a liquid far below Tc, close to the glass transition temperature. And what you see here, you have this plateau-like region which marks the yield stress. And then eventually at very, very low shear rates, you would expect that there's a Newtonian fluid state. And what I would like to study here is, can one access such states? So say one is essentially, one has this pronounced plateau, can one access states in the simulation here? And to this end, we use swap Monte Carlo. In this, my second theme is on microeology. There we pull a particle through the system with a constant force. And the question that I would like to address is, if one is in a deeply supercooled state, so can one describe this in any way? Is there the existence of a depinning force? So which would be an analogy to the yield stress here in this case for the macroeological case. And so does one see a kind of depinning transition on transient timescales? Okay, in order to get to these themes, so what we need is we have to have a system where we can apply the swap Monte Carlo technique. And here I present a modified Cope-Anderson binary Lennard-Jones mixture model. So I just make it polydisperse. And then this allows to apply the swap Monte Carlo technique. And I will also discuss the differences in this first part between the original binary mixture and this polydispersed version of it. And then I come to the two themes, so to the macroeology and the microeology. Okay. So to access equilibrium states far below Tc, a nice technique that one can unfortunately only apply to polydispersed systems is the swap Monte Carlo technique. So when one has a polydispersed system, one chooses randomly a pair of particles and then one swaps their diameters. And one can introduce a dynamic scheme, so where one combines the swap Monte Carlo with molecular dynamics. So every so-and-so MD steps, one performs several swap sweeps, and with this one gets a fast method to get to equilibrium states, so which are far below Tc and close to the experimental glass transition temperature. Okay. Now, what I use throughout my talk here is the Cope-Anderson binary Lennard-Jones mixture. So this is a binary mixture, 80-20. It was originally, you can see it as a model for nickel 80, phosphorus 20. And so these are the energy parameters. It's you have a non-additive mixing rule here, which one can write like this. Now, one can make this Cope-Anderson mixture now polydisperse, and we do it in the following manner. So we use a polydispersity for the B particles and the A particles. And so this can be described, so we assign to each particle in a uniform manner and in a deterministic manner a diameter via these rules here, and there's only one parameter with which one can control the polydispersity for both A and B particles. And then we use the same mixing rule as in the original model. So we perform the swap Monte Carlo for this polydisperse Cope-Anderson-Lennard-Jones mixture. And we choose for this value of gamma 0.06, which, what was this? Which means that the width is of these distributions here, of the diameter distribution, is such that they meet each other here. So they have. We have a relatively broad distribution. We work at a density of 1.3. TC there is around 0.65, and the class transition temperature with the swap dynamics is at 0.48. Now we can compare the polydisperse variant with the original binary system, and this is first of all the potential energy as a function of temperature. Of course, we get to much lower states in equilibrium here with the polydisperse version in blue. These are the blue data points. And we see that the potential energy per particle is very similar to the original binary system. So if one takes the ratio in this area here, so it's slightly above 1. Now we have also applied a thermodynamic integration scheme and computed the free energy difference between the polydisperse mixture and the original binary mixture. And so here what comes out, so this is the free energy difference. Of course, the energy difference is very small, and what is mainly contributing here, so the main difference is in the entropy. So there's the entropy difference between the polydisperse and the binary system. And this is, at least in this temperature range, pretty constant. And also the relaxation time, so the polydisperse system is slightly faster, but the ratio of relaxation times is more or less constant in this area. So we can expect that the polydisperse system is, with respect to the physical properties, is very similar to the original binary Lennard-Jones mixture. And now we can apply the hybrid swap Monte Carlo MD technique. And this we will apply now for systems under shear. So this is my next theme. And so there has been, it has been proposed this is a work from the YIP group, that to get access to states, so for systems under shear at extremely low shear rates. And what they used for this is, so they combined their molecular dynamics with a kind of metadynamics. And so they demonstrated this here in this paper. So they got really here, these are very small shear rates. But there are problems with this technique. So I have friends who tried to reproduce these results, and they failed somewhat. They were not able to reproduce their results. And of course, what is also difficult is, so they have some phenomenological formulas, approaches to assign to these states they obtain via metadynamics an effective shear rate. And so what we want to study is, can one really, so in which region of here, so in the here, this would be correspond to the linear response, then here in the nonlinear response regime, where can we really get states at extremely low shear rates? Yes?
Sorry, just because since you mentioned the work of Yip et al. Yeah. No, just can you clarify to people, including me, what kind of simulations are they doing? What is the basis of their estimate? Meaning, these shear rates are not things that you actually produce.
Exactly.
Right. So how are they?
No, they use metadynamics, combine it with the MD under shear, and so then they have some theory with which they assign these effective shear rates to these states. It's not. It's very phenomenological and heuristic how they do that.
But in any case, they don't actually do a simulation at these low shear rates.
No, it's just, so they do the simulation with metadynamics, they get to some states, and then they say, okay, these states correspond to these shear rates they got. Okay, so we want to do something similar, so we use planar Couette flow, as they did also. And so in planar Couette flow, you approach in the steady state a linear velocity profile, and in the linear response regime, you can read off the shear viscosity. Some details of our simulation: we shear the system using these Edwards boundary conditions in combination with the DPD thermostat. We don't introduce any slot equations or so. And this is a typical result. So this is the stress-strain relation now for the Cobb-Anderson mixture at density 1.2. And here, so the lowest shear rate at this temperature reflects the Newtonian response. Here we are in the linear response regime. And as we get to the nonlinear response, we have the emergence of this overshoot, which marks, this occurs around the strain of 0.1. And it marks the transition to plastic flow. Okay, so here are flow curves. So we can now read off the steady state stress, of course at very, very large strains, and plot it as a function of the strain rate. And this is now for the density 1.3, different examples. So TC is here at 0.65. This is a very low temperature at 0.54, and here 0.75. At 0.75, we have access to the Newtonian regime. So we have here a linear relationship between the steady state stress and the shear rate. And at the lowest temperature here, we get the typical Herschel-Bulkley behavior, where we can read off via this fit here, yield stress, and the exponent is here around 0.5. Okay, question is, when we, for instance, consider this temperature here, to how small shear rates do we have to go in order to see a Newtonian response? So with this one can try a wild estimate of this. And this is done via the stress-strain relations. So the order parameter for the non-Newtonian regime is the emergence of this stress overshoot. And we can measure this. And so the distance from the maximum to the steady state stress, this is some value of delta. And if this delta disappears, we reach strain rates, and below these strain or shear rates, we can expect that we obtain a Newtonian response. And this we do here. Of course, for 0.75, we have access to the Newtonian regime, and we see that we plot this delta as a function of the shear rate. So we see that we land here at a shear rate of the order of 10 to the minus 4. And so below here, so we expect a Newtonian response. We can do the same at 0.54, and then we are here, and then for over many order of magnitudes, we would land here at 10 to the minus 11, so the extremely low shear rate. Now the question is, can we get access, as a proof of concept, can we get access to states which are below these strain rates? And to this end, we combine our molecular dynamics, non-equilibrium electrodynamics under shear with swap Monte Carlo. So we do the system with the simulation under shear, and from time to time we introduce the swap moves. It's a kind of like we interrupt the simulation and do a kind of energy minimization, if you like. Okay. And this is what we get. So this is, first of all, at a temperature of 0.75. It's very large. And this is via straightforward MD, and this is via the hybrid scheme. And we get states here at very low stresses. This is now at temperature 0.54. And in fact, with the hybrid scheme, we get to stresses, and the response looks very, very Newtonian-like. which are far below the yield stress, in this case, that we have estimated before from the Herschel-Barclay fit. So the question is, these states that we get there, are they, to what, so this is the question, to what extent are they affected by the swap dynamics, or to what extent are they, can one assign similar states in a direct MD simulation? And to this, yes.
No, so you could have validated that with the higher temperature simulations, right?
Yeah,
You've done that. Yeah.
I come to this in a moment, yeah. And a good quantity to validate this is the potential energy per particle. So this is the potential energy per particle as a function of the steady state shear stress. And this is first of all at high temperatures. And these points are from the ND simulations, and this is from the hybrid simulation. And we see we have agreement here at low steady state stresses, and this corresponds to low shear rates in this case. However, if we would go to larger stresses here, we would see deviations from this curve. So we get to different energies and therefore to different states in the nonlinear regime. Now, this is also the case at the low temperature, but here we can expect, so this is the potential energy at zero stress, so with no shear. So we can expect that we here, with these states, we are close to the steady state. So in fact, we can, via this hybrid approach, we can generate states at very low shear rates. So what we can say is that this is at least below the shear rates where we would still have a nonlinear response. Okay. Then I come to active microrheology. So first of all, here we go back to the original binary Lennard-Jones mixture. So this is just MSDs for the Cope-Anderson mixture, and from this the self-diffusion constants as function as inverse temperature. And so we are interested in the microrheological response around these temperatures here, so around TC, and the lowest temperature in the following will be 0.6. So we use this geometry and apply the microrheology. So we just take a single particle and pull it through the system via a constant force Fx in x direction. And so in order to get a reasonable statistic, we have to take averages over of the order of 1,000 to 1,500 trajectories. And again, we use a DPD thermostat in this case. Okay, first of all, what do we expect in the linear response regime in this case? So we pull the particle with the constant force, and we obtain, after some time, a stationary state where we see a constant velocity of the particle. And so we have F is proportional then to the stationary state, steady state velocity, and this proportionality factor is the friction coefficient. Actually, a similar experiment has been done with magnetic beads a long time ago by Habdas et al., so in the Weeks group. Now, in the linear response regime, we have an exact result which relates this friction coefficient with the self-diffusion coefficient in equilibrium. And so this is an example of a fluctuation dissipation theorem. So here, the self-diffusion coefficient is given by kBt divided by xi. And so here I show examples, so here and here, where we are in the linear response regime. So this is the displacement as a function of time. And so this is at the temperature 1, force 5. And so if we wait long enough, we approach the stationary regime from which we can read off the mean velocity, the average velocity. And so via this steady state velocity, we can then determine the friction coefficient, and this is now shown here as a function of force. So here we have with this force, this is this example F equal 5, we are close to the linear response regime. So this point is computed from the self-diffusion coefficient. And then we have this decrease, which marks the, as a function of force, which marks the nonlinear response. And in fact, if we go to this point here, where we are close to the linear response, so all the MSDs, so this is the corrected for in force direction, it's corrected by the drift motion. So this we subtract here. And in force direction, all the MSDs agree with that obtained in equilibrium. Now, interesting now is this nonlinear response regime. And this shows different displacements as a function of time for temperature 0.68. And we vary the force from 5 to 50 here. And the corresponding, so then we can read off in the stationary, so at long times, the steady state velocity, and from this the friction coefficient, and the corresponding curve as a function of force is shown here. Okay, now this is for different temperatures, and we see, first of all, that this linear response regime moves to smaller and smaller forces. So this regime where we see a linear response with decreasing temperature becomes narrower and narrower. And now it's interesting, how can we characterize these the stationary states in the nonlinear response regime? And one very exciting result here, and this is a kind of fingerprint of microgeology, is here the MSD. So then again, this is the MSD in force direction corrected by the drift motion. And so again, for this temperature 0.68. And we see, so this is for comparison, the equilibrium curve. So first of all, these curves at finite force agree with the equilibrium curve, and then we have this deviation. And what is remarkable, the exponent here, the long time behavior is not linear, but superlinear. So we have a super diffusive motion at long times here. And the exponent increases with force, so, and it reaches here a plateau at around 1.5, 3.5. And then at very large forces, it will decrease again, and we get back to normal diffusion. And these stationary states where we have this super diffusion have no analog in, say, class-forming liquids under shear. So this is really something unique in microgeology. So we can now ask, so what happens here? So how do the trajectories, for instance, look like if we go to the nonlinear response regime and we are here at these states where we have superdiffusion? And these are typical trajectories from the simulation at different temperatures. So here, relatively high temperature, here 0.68, the example that I've shown before, and then we go to lower temperatures, here down to 0.6. And what is remarkable here, we have the occurrence of very mobile trajectories. The particles are very mobile, and at the same time, so those particles who are completely localized. So over the whole time span here. So which means we have the occurrence of two populations, and this becomes more and more pronounced with decreasing temperature. And so localized and very mobile trajectories. And now we can quantify the fraction of these localized trajectories. And one way of doing this is, here this is the displacement as a function of time. And we can just introduce a cutoff here and say all what is below the cutoff is immobile, and all above is mobile. And then we can determine the fraction of trajectories, so here denoted by eta, that are mobile. And here are the results for this, again for different temperatures. And it's most pronounced here at the lowest temperature. We see that at low temperature and low forces, we have the emergence of this plateau, and we have to wait some time, and then it shoots up. Then all the particles become localized. And so what one can ask is this: can one relate this to some depinning scenario. And I would say no, at these finite temperatures, it's a matter of the time scale, at which you reach at any finite force, at which you reach the mobile, so the stationary state. So one can also consider the Van Hove correlation function. So this is now also at the low temperature in comparison to the equilibrium system. So this is at F equal 10 and at F equal 25. And there what you see is very pronounced. You have these localized particles. So this is the central peak here. And then at long times, the very mobile particles, which is reflected by these tails here. Now one can do the opposite and determine the fraction of localized particles and how they decay as a function of time. This we do here. So we determine, so we make fits with the Gauss function over the central peak, and we determine from this the fraction of localized tracer particles at time t, and this we call pi of t. And this is shown here. So it's a decaying function. So it decays. It's slower the smaller the force is, and now we can read off a characteristic time scale here and scale it with this time scale, and then the different curves fall more or less on a master curve. And so when we plot this time scale as a function of force for different temperatures, we see an exponential decay. But we have always an upper bound here, which is the relaxation time that we would expect in equilibrium. And this means, so we cannot have in the supercooled liquid at least the pure depinning scenarios, because it's always here restricted by this time scale, which is corresponds to the structural relaxation time in equilibrium. So I come to the conclusions. I presented two themes. One, macroeology. This was a proof of concept, the emergence of a yield stress of so we have we see that we can have access to Newtonian fluids at very low shear rates by applying a hybrid swap Monte Carlo MD technique. And then here for the microeology, so the characteristics is in this intermittent behavior of the trajectories, so so that we have two populations, mobile and immobile particles. Thank you very much for your attention.
So, Misaki.
Hello. I may misunderstood. Maybe I misunderstood, but so what I understood is that you can get. So I'm talking about the first part of your talk concerning about flow curve. So as far as I understood, so with this MD swap combined method gives you the flow curve of the same flow curve as the pure MD, even if the shear rate is small. This is your statement? Okay, so this is
but only the linear response.
Okay, but this is a bit mysterious because we know that without shear, the dynamics of swap type dynamics, the relaxation time is significantly faster than the standard MD.
Right.
Okay. At the same time, we know that the viscosity and the relaxation time is more or less proportional to each other.
Yeah.
Okay. So this means that somehow I would expect your flow curve is sort of effective flow curve give rise to much smaller viscosity at the small shear rate regime, instead of having exactly the same value as the standard MD.
No, what we can say is we can assign to these states an effective shear rate, and this effective shear rate would correspond to the say pure MD case. What I claim is the stationary states I get with the hybrid scheme, and that I would get with the MD at this very low shear rates are the same.
Okay, so you have effective shear rate that
Exactly.
absorb this difference.
Exactly.
Okay,
Yeah.
okay, thank you.
Okay, and how are you estimating that? I'm sorry, I missed that point. The effective shear rate, where does that come from?
No. So all I'm saying is, so here one gets some states with a certain steady state stress. And what I'm saying is, so this is via the hybrid scheme. And what I'm saying is one would get the same stationary states if I would perform MD simulation at a very low shear rates in the Newtonian regime.
But you don't know what that shear rate is.
I don't know what that shear rate is. So I can only say this corresponds to such a state, yeah.
So for the first part, maybe it's a stupid question. So what is the meaning of temperature? Because we are driving the system, it's anyway out of equilibrium. So why you are equilibrating it?
What do you mean?
You are shearing it with a finite rate.
Yeah,
The system
yeah.
is out of equilibrium, right?
Yes, that's right. But what we so the issue is the initial configuration is just equilibrated at this, for instance, this temperature here.
So it's
so one would not expect the stationary state does not depend on how well annealed this is, the state is.
I was asking about during the shear,
yeah.
when you apply this, you are equilibrating using DPT or something.
Yes, yeah. No, it's thermostated by DPT.
Okay, there is another question about the second part. So you mentioned the fluctuation, which is beyond linear this thing for the direction in which you are driving. What about the perpendicular fluctuation? Is it still?
This is diffusive still. Okay, of course, it's also different from the equilibrium diffusion, but it's diffusive. Yeah.
Thanks.
Okay, are there any more questions? Yeah.
So maybe I missed it, but did you show how the viscosity depends on temperature for the first, in the first case?
So I have not shown this. So what I've shown is the flow curve here. Yeah. And I just if you divide this by gamma dot, then you have the viscosity as a function.
Yeah, so how it depends on the temperature?
So here you have, this corresponds to a pronounced shear thinning, of course. So here at low temperature, and here you have the, So
I just wondering how it increases with temperature when you decrease the temperature.
Yeah, in principle, it's similar to the self-diffusion coefficient or so, and you have the usual violation of Stokes-Einstein relation and so on. But we didn't go into this.
Okay.
Okay, Paddy, last question.
So, Juergen, I'm going to put my experimentalist's hat on and ask about the experimental references that you made. So you said that there was some early work, I think it was in the Eric Weeks group. Did they measure the force that they were dragging the particle with?
Yes. So this is at constant force, yeah.
Okay, and then there was later work from the Frank Sheffield group. Did they measure the force?
Yes.
The polystyrene particles were in tweezers.
Yeah,
okay.
Yeah.
So in both of these cases, there's a solvent. Does it matter?
There's what?
There's a solvent. In
there's
both
a solvent.
The cases,
yeah.
both
There's
of
a
the
solvent. In both cases, there's a solvent.
Does it matter in terms of quantitative comparison with what you have? Can you make quantitative comparison with what you have?
So I'm not able to introduce explicitly hydrodynamic interactions or so, but one can do the same with Brownian dynamics too, and one gets similar results. Yes. It's just to the experimentalists, one warning is, so in this case, one could also drive it via optical tweezers with a constant velocity. And this does not correspond to there you don't have a linear response regime, which is well defined, because what you get in the stationary state is a state where the mean squared displacement would be flat, it would be a constant, and it reflects just the motion of the particle in the tweezer potential. So it's, in some sense, so the microreology at constant velocity does not correspond to the macroreology at constant shear rate. These are two different things.
Thank you.
Okay, so with that, let's thank Juergen for a very interesting talk. So we break for coffee now, and we return at 11:45. And before each break, Ranjini will have an announcement.
Yes, yes. So here's the update number 1. So many Apple users might see that you're unable to connect